constrained maximization, Lagrange multiplier method. I should rather say constrained optimization. So if you remember, we have done this guy last time. We have done the maxima and minima of the function of several variables. But all of this was without any constraint. That was unconstrained optimization. So we found out the maxima or minima of functions of several variables without any constraint. But there can be the cases when there is certain constraint which is put on the value of x's, right? So how do we find out the solution there? So this is a very intuitive explanation for the Lagrange multiplier method. So I'll be giving examples maybe in the other class, but you should understand why we are doing this cookbook procedure. I mean, how do we actually do it? And if possible, even why we do it. So this is not a very mathematical recording. We are not going into hugely mathematical explanation for Lagrange multiplier method. I am just telling you that much which is required for me in my course. That is it, right? So beta, when there is an unconstrained optimization or unconstrained maximum, right? So it means you have an optimum value. You are trying to find out the optimum value without any constraint, which is put on the independent variables. Optimum value without any restriction. On choices of x's, right? But there are possibilities, beta, where not all choices of x's are feasible. For example, I am a consumer and I want to maximize my utility. I will be consuming goods. So by consuming goods, I get certain utility. But I mean, I can't say that any value of x is feasible. You have to restrict the domain. How? That is, you will be saying only x's which are from 0 to infinity that is allowed. Let us say like that. So the negative value of x won't help. So sometimes all choices of x's are not feasible. So it gives the reason why we have to look for the constraint optimization. In unconstrained optimization, there is no constraint on x's. But there is a possibility that not all x's can be feasible. Not all x's can be feasible. So x can be positive. X can be positive. X can be 0, but x can't be negative in case of the consumer optimization problem. Or x can be, for example, you are doing the profit maximization problem. So your output can be positive, output can be 0, but output can't be negative, right? So for example, profit maximization problem. Or utility maximization problem. In any of these, I mean, if you get the value of x which is negative, that is meaningless, right? So negative x is not allowed. And it is not, I mean, more than not allowed, it is not having any meaning. Negative x is not. So in these kind of problems, where not all values of x's are allowed, in these kind of problems are called the constrained. Optimization problem. Right. Where the x's can be constrained, that only positive x's are allowed. Only x from 0 to infinity is allowed. Non-negative x's are allowed. Right. So, I mean, for example, I would want to consume anything. Not only that, I mean, in the utility maximization problem, don't you think that I am also constrained by my income? I would want to consume the infinite amount of x's, but can I consume infinite amount of x's? No, I can't. I mean, I'm constrained by my income. So when I'm constrained by my income, that is also your constraint optimization problem, right? So, for example, individual is constrained by income or budget. Income or budget, right? Now, there can be constraints which are binding. There can be constraints which are binding, right? So when you bind the constraint, when your constraint is binding, it would mean that the value of your function, which could have been maximized without this constraint, would have been more as compared to the situation when you have constrained it, right? When you have constrained it, हमारे पास जो वैल्यू ऑफ द फंक्शन है, कोई भी f है, अगर हम उसको बिना किसी कंस्ट्रेंट के मैक्सिमाइज करते तो हमारे पास ज्यादा वैल्यू आती उसकी एज कंपेयर टू जब हमने कोई कंस्ट्रेंट पुट कर दिया है. ठीक है. सो बाइंडिंग कंस्ट्रेंट्स, दे लोअर the value of function being maximized, right? And why it happens? Because you cannot just freely choose among any x's which are available, because we are not able to choose among all x's. Right? So the value of the function fx is not as large as it could be. Is not as large as it would be. And then you have non-binding constraint. So non-binding constraint is going to be the one where the value of the function is going to be the same as it would have been if there would have been an unconstrained optimization. तो जो वैल्यू तुम्हारे को बिना कंस्ट्रेंट रख के आती, वही वैल्यू कंस्ट्रेंट रख के भी आ रही है, तो उस कंस्ट्रेंट का कोई अर्थ ही नहीं है, राइट? So the value of the function which you are getting from the constraint optimization is same as the value of the function which you are getting from the unconstrained optimization. Then this is not a binding constraint, right? So the constraint, this will be more clear when I'll give you a few examples, but let me just write the theory behind this. The constraint would be non-binding if we could obtain the same level of effects with or without imposing the constraint. Without imposing the constraint, right? So what I'm saying is, with imposing a constraint, it's a constraint optimization, and you get certain value of fx. If that value of fx is same as the value of fx which you are getting without imposing the constraint, to problem. So that is the non-binding constraint. I'll give you a few examples, but let me just tell you the theory, right? So maybe in some other in other recording, I'll be telling you that. So we know about the maximization and minimization of functions of several variables. Yes, right. We also know that at the optimal point, all the partial derivatives, they have to be equal to 0. Yes. Kara tha na? In the earlier recording, we have said, okay, if your y is equal to f of x1, x2, and so on to xn, hai na? This is the function of several variables. Then del y by del x1 should be equal to 0 at the optimal point. Del y by del x2 equals to 0, and so on to del y by del xn equals to 0, and so on to del y by del xn equals to 0. Ye sare ke sare, they should be all equal to 0. So we had, these are n equations, na? And you have n variables. So these n equations in n variables, they could be solved together. Yes. So, but when x's are constrained, there is one additional equation. So this is the case of the unconstrained optimization. But when x's are constrained, there is one additional equation. What is that equation? Constraint equation. But x's are constrained. So we have one additional equation. Right? Okay. We have one additional equation. What is that additional equation? Constraint equation. How many variables you have? You still have just n variables. But how many equations you have? N plus 1. So you have n+1 equations but you have n variables. So don't you think that these set of equations are overdetermined? Means you have more number of equations and less variables. More number of equations and less variables. Yes. So what is this method telling? This method is telling you the problem is this, that you have n+1 equations, but you have n variables. So if I can introduce one more variable, then I will also have n+1 variables now. If I can somehow introduce one more variable, then I will have n+1 variables now, right? So Lagrange multiplier method says we will introduce one more variable, right? Which is the Lagrange multiplier, that is lambda, in solving this problem. So you will have n+1 equations then, and you will have n+1 variables. So what I'm saying is, जैसे यहाँ पे you have these n equations ना, we will introduce one more equation. What is that? I mean, it should not be y, I should not be writing like this. But you will have how many variables? You have n x variables plus one Lagrange multiplier. Okay? So what do you have? So beta g, you have y is equal to f of x1, x2, and so on to xn. Okay? Subject, you want to maximize this. Let's say subject to gx1, x2, xn equals to 0, like this. Right? So what you do is that you form this Lagrangian equation. How do we write this? We will write it like this. F of x1 x2 so on to xn plus lambda gx1 so on to xn. हाँ जी बेटा. And this gx1 xn तो ये तो 0 ही है. That's what the condition is. So this lambda is the additional variable. So you have n x's, right? There were n variables. This lambda is the additional variable. Anji beta, this lambda is the additional variable. Yes. When the constraint is holding, so beta this to ye to 0 hi tha na, subject to this thing. So this is going to be when constraint holds. Equals to 0 hai. If constraint, of course, constraint is holding because we are saying that this is going to hold at G, this constraint is going to hold, you have to maximize this subject to this constraint. So beta, agar ye 0 hi hai, then whether you maximize L or you maximize F, that means one and the same thing. This is 0 na. So whether you maximize L or you maximize F, that is one and the same thing. Yes. So if we are going to restrict our attention only to those values of X which are satisfying the constraint, So whether you maximize f or you maximize L, that means one and the same thing. Maximizing f would mean what? You need to find del f by del x1, del f by del x2, del f by del xn. Maximizing L would mean what? Of course, finding all of this, del f by del x1 equal to 0, del f by del x2 plus this thing also. यहाँ पे भी है ना x तो मतलब maximizing L के लिए मुझे क्या चाहिए? Del L by del x1 equals to 0, del L by del x2 equals to 0, and so on to del L by del xn equals to 0. एक बार और सुनेंगे. If I'm going to restrict my attention to only those values of x's where constraint is being satisfied, then this constraint is holding, and in that case, gx1, x2, and so on to xn is equal to 0. That is what my constraint is, right? Agar ye 0 hi hai beta, then whether I maximize L or I maximize F, that means one and the same thing, right? Optimal, in order to find out optimal, you know, these partial derivatives have to be simultaneously equal to 0, right? So if I just maximize L, so del L by del x1, kahan pe x1? X1 is here, x1 is here. So how do I write this? Del F by del x1 plus lambda del G by del x1 equals to 0. सही बात? Del L by del x2 is del F by del x2. x2 कहाँ पे है बेटा? यहाँ पे, and x2 is here. Del G by del x2 equals to 0, right? Then del L by del xn is del F by del xn plus lambda del G by del xn equals to 0. And there is one more expression, which is what? Del L by del lambda. Del L by del lambda, which is what? कहाँ पे बेटा lambda? Lambda तो सिर्फ यहीं पे है. So what is that? That is gx1 and so on to xn equals to 0. Lambda is also the variable. You've introduced one more variable. Why? Because you want to have n plus 1 variables for n plus 1 equation. So how many partial derivatives you have? N plus 1. So these equations, they have to be solved simultaneously, right? So these are the conditions. These are the conditions for critical point of function L. So these are n plus 1 equations in n plus 1 variables. So there are n x's plus 1 Lagrange multiplier. They couldn't be solved. इतनी सी ही बात थी ना, that in the unconstrained optimization क्या करना था? In the unconstrained optimization, this del F by del x1, del F by del x2, all of them, they have to be simultaneously equal to 0. In the constrained optimization, you have one more expression, and you will be writing the Lagrange in this. You write the function plus Lagrange multiplier into the constraint like this. So this is the theory behind this thing, and these are the necessary conditions. I'm not going into the second order conditions for the Lagrange multiplier and all this. अभी नहीं जा रहे हम, बस इतना भर के लिए. So we this is going to give us the solution to these expressions are going to give us the optimal value, assuming that the second order condition of holding हम नहीं जा रहे थे उसमें. बस इतना भर समझिए, right? I'll give you 1 or 2 examples for the Lagrange multiplier in the next recording, right, beta? So you read it carefully and you write notes alongside, you will be able to understand. Thank you, beta.